is my pleasure to introduce the second speaker, Dr. Jamie Walton from University of Nottingham. His work was already mentioned together with his assistants in the previous talk by Professor Goodman Strauss, and he's going to talk about hexagonal aperiodic set of tiles, and in the spirit of Robin Knight, who says that 4 colors suffice. With Jamie, in Jamie's talk, we'll say that 1 screen suffices.
Okay, well, thank you very much. Many thanks again to the organisers. It's been such a joyous conference. I've loved it so far. I'm slightly wondering why I've been asked to talk. I think anything I can speak about is necessarily going to be quite old hat. Sorry. So you've all seen this picture many times now. This is the main guide of this conference, the hat tile. Very beautiful. I haven't done any work really on hat tiling. I can't tell you anything that the experts can't tell you. So I was wondering what I should talk about. And one notable feature of this is that it lives over the hex grid. And I've done a little bit of work with Mike on hexagonal aperiodic tile sets. I thought this would be a natural fit for this conference because a lot of people in the room who like to know how things fit together and force aperiodicity at large scales. I should maybe mention that between the discovery of the hat and Penrose's tiles, there's a big gap in time. It's very simplistic and easy for the media to say, oh, there's this dry spell between 2 and 1. That's very easy to say, but it's completely false. There's been a huge amount of activity between those times. Other really beautiful examples of tiles, and just the study of these objects, their global structure, their long-range structure. We now have a huge amount of sets of tools for studying these things, these completed patterns through algebraic topology, for example, dynamical systems, ergodic theory. And I think it's amazing that these tools are in such a state now that we can say so much about this hat tiling within a few months of it being discovered. So the recent paper of Baco, Gala and Savoon is, I don't know, he was been burning midnight oil to get this out, but it's we already know so much about it through these tools. Anyway, I want to talk about something a bit simpler. I just want to showcase 3, what I think are quite nice hexagonal monotiles. I say monotiles with some apostrophes. It depends on your rules, of course. What you count as a monotile has been described very thoroughly in the last talk by Kine. So I'm going to showcase these 3 tiles. We've got the Penrose 1 plus epsilon squared tilings. So these aren't the pentagonal based ones. They're not as well known, but I thought I'd like to advertise them at this conference. We have the Socolar tilings, which have been talked about quite a lot. And I wanted to quickly describe this tile with Mike, where we have these charged edge decorations. The main reason I wanted to talk about that is that, as also has been said a few times so far in this conference, we really don't have that many methods of proof for aperiodicity. So we have this huge zoo of really beautiful examples, but the proofs tend to come down to this composition, decomposition method, the hierarchy, and so on. And one amazing thing about the hat tiling is that we learned this new approach for proving aperiodicity, but nonetheless, the list of approaches to proving aperiodicity remains pretty small. And we've got a really simple proof that I feel is quite distinct for this one. So I thought people might be interested in seeing the proof of aperiodicity of this tile. There's a fantastic analysis and comparison of these 2 tilings here, the Penrose 1 plus epsilon squared and the Taylor Socolar tilings. They look very, very similar. And I think Michael was saying there was a bit of a challenge from Penrose to show that they really are distinct tilings. They're very similar, and have a lot of similar structures, but actually they are, one is not simply a redecoration of the other. They are distinct tilings. And there's this really nice paper which does a similar beautiful analysis of the dynamics and topology of these tilings. So one of the messages I want to convey throughout the talk, though, is that although these 3 tilings here, they have the theme of hexagon-based aperiodic tile sets, and they consist of a small number of tiles, which is also true for the new hat tiling, just 1 tile, and based on hexagons. Actually, structurally, the hat is completely different. So I think that only emphasises what a remarkable achievement the hat was. It's not simply based off these ones, it's completely new. There's no way of linking the structures of these at all. Okay, So let me start with quickly describing the Penrose double hexagon, or 1 plus epsilon squared tile. So yeah, not quite so well known as these other tiles, but also very beautiful. We have this hexagon here with marked edges, and as you can imagine, we must place these so that the edges match with the arrows match on the edges. But we also have this vertex rule. So once you've pieced together your tiling, you have to be able to put these smaller pieces onto the vertices. And you can see that the arrows, there are 2 on opposite edges which point in the same direction, and all the others face in opposite directions. They point to these 2 vertices here and here. These 2 point just to the left, and there's a similar structure here with these corner pieces. So you can think of those as extra pieces, but you can also just think, well, around the vertex, can I fill it in or not? So you can think of it as not an extra tile, but as a sort of a rule that you have to check. Although it's not quite a vertex rule, because you need the vertices to be consistent with each other as well. You need to be able to consistently assign the edges between them. So it's very much pushing the rules here for if we can call it a monotile or not, but it's a nice example. And as I indicated, those matching rules, you could instead convert those into little tiles. So this is where the name 1 plus epsilon squared comes from. Primarily, this is a hexagonal tiling. So the bulk of it is really a hex tiling, but you also have these arbitrarily thin shapes, which we think of as the epsilon. So you can make those arbitrarily small in area, scaling of epsilon, because they can be arbitrarily thin but have a given width. And then you have these other kind of key tiles of the epsilon squared ones, the vertices. And it can be generated by a substitution, as shown in this picture here. And you can use that to understand the long range structure quite well. We've also heard a lot this past couple of days on the Socolar tile, so I don't need to do too much work to remind you of how this works. So we have a single tile. We're allowed to use reflections. I should have said that for the previous one we use reflections, rotations, translations. The same for the Socolar tile. We have these black edge decorations. Those are required to meet over edges consistently. But we also have this other rule that communicates to next nearest neighbour tiles. So whenever you have 2 tiles meeting, when you have 2 tiles opposite each other and 2 vertices separated by an edge, well, the flags at those vertices need to be pointing in the same direction. So those are the 2 rules for the Socolar tile. Now, of course, it's not ideal that it communicates between non-adjacent edges, but from the perspective of shift to finite type, it's still quite a nice setup, and you can see that the global structure is very, very simple to understand. It forces this hierarchy of beautiful Sierpinski-like triangles. You can make it entirely geometric. I think this has also been said. You can make it entirely geometric, but the cost is that you have a much more complicated shape of tile. I think I heard people say that it has to be disconnected, but actually you can make it from a connected tile, but only one which has non-connected interior. In other words, it has these cut points. So each region here of a single colour is one tile. And these can also be generated by a substitution procedure. Actually, the substitution defines a minimal core which excludes 2 tilings which you can also build that have defects. This happens also for the normal Penrose tilings. There's an illegal patch that you can start with, a seed, and from that there's only a unique tiling that you can build out from it. A similar thing happens for the Socolar tile. There's a defect which you can rule out with 1 extra rule at a vertex forbidding 3 flags of the same handedness. So similar structures there. Now, both of these are very closely related to the array half-hex, which in turn factors to the half-hex. So I wanted to quickly show off this substitution. I think we've also seen this one before in Natalie's talk, as I remember. So let me just iterate this substitution a few times. So you can see when I substitute, every half-hex is paired up with another one. So actually you can join them together to make a hexagonal tiling. So you can think of this as a hex tiling where we have 3 different kinds of decorations on the hexagons given by these lines that can be in 3 different orientations. So that's the half-hex substitution, and you can, if you want to work with hexagons rather than half-hexes, you can work with this substitution rule here. Now, there's that patch again, which I generated through the half-hex substitution. I find it a bit tricky to look at this and to see the structure. You can kind of see little features, But I'm going to do something very simple. Just take each of these lines and rotate them by 90 degrees. If you do that, well, at least I can see a lot more structure here. You can see these Sierpinski-like triangles more easily. So, for example, that one. Although I've chosen, when drawing that, to offset the lines in one direction or another. So, we're going to talk about the arid half-hex, which gives you these Sierpinski-like decorations. And what the arid half-hex does is it tells you which way to offset these lines to make these hierarchies of Sierpinski triangles. So let me show you that. So here's the unarid version, just the normal half-hex. Here's the arid half-hex substitution. So to determine these offsets, these lines, to draw these Sierpinski triangles, we have these arrows. Now, another way of thinking about that is I can add these edge decorations. So I'll flick between these so you can kind of see the comparison. The arrow is pointing in the direction where I've got the two opposite edges, which are pointing in the same way. Okay, so you can see the comparison there. And also note that the edge decorations here are as for the Penrose 1 plus epsilon squared. So if I take a completed such Penrose 1 plus epsilon squared tiling and remove the vertex decorations, then I obtain a tiling like this. Now, these little arrows, they also, you can think of them as pointing towards the where the line decorations for the Sierpinski-like patterns, where they intersect the edges. So let me flick between those. You can see the arrows are pointing to where these blue lines are exiting each edge. Okay, so let me show you how this looks if I take one of these tiles and then I iteratively substitute it. So there's level 1, level 2, 3, and 4. And you can see these beautiful Sierpinski triangles. Okay, so this single marked tile is a nice base unit for trying to construct aperiodic tilings. Of course, if I just start with this tile here, I can make periodic ones with it. Let me quickly discuss what you can do with it when you start trying to put it next to itself. So one thing that I could do is just keep using straight edges like that. I can build infinite edges. But if you don't, there's going to be a turn at some point. So maybe around there's a turn. And then, well, then I can put straight edges, and I can have a bi-infinite line with a single turn in it. That's allowed. What else can happen? Well, I could have another turn. Notice that I always have to turn in the same direction because of the offset. So if I think about traveling to the left here, I'm always going to be going anti-clockwise around these triangles. So if I turn twice, you can see that if I extended this line down here, well, I'd run into problems. What would I put? I'd be crashing into this line here. So I need to close that off to a turn there. So there are only three things that can happen. If I start one of these lines, it can be a bi-infinite line, it can be a bi-infinite line with a turn, or they form these closed triangles. Those are the only things that can happen. And actually, with a little bit of work, it's quite a fun exercise to show that if you start with the exterior of a triangle, there's a unique way to fill it, and it's this Sierpinski-like pattern. And that also limits the dimensions of these triangles. They have to have 2 to the n plus 1 tiles along each edge or something like that. That's not actually going to be important for what comes later. Okay, so it's not a monotile, an aperiodic monotile though. So you can, of course, build periodic targets with this. There's an example. So this is not an aperiodic monotile, but I don't know if this sentence has much meaning, but I feel like it's kind of close to a monotile. Because all you need to do to make this a monotile is to force triangles of arbitrarily large size. If you force triangles of arbitrarily large size, then you're going to get something that's aperiodic, because any fixed finite translation is required to map triangles onto other triangles. Well, once your triangles are bigger than the size of that translation, you're going to get non-trivial overlap between the triangles, which means you haven't preserved the pattern. So, how can we force arbitrarily large triangles? Well, the Penrose 1 plus epsilon squared is one such way of decorating these to force arbitrarily large triangles, and the Socolar is another very nice way. With Mike, we wanted to think of other ways of doing it, using simple edge-to-edge rules, and we came up with this. So here we have a arid half-hex tile, but with these extra funny decorations on them, and we should think of these as charges. I've got 3 plus charges on the right and 3 negative ones on the left. And each of them have clockwise or anti-clockwise or both indications on them. So here I've got an anti-clockwise, both anti-clockwise and clockwise, and here a clockwise one, and similarly around that side. And here is the rules. Here are the rules. The first one is, of course, that the decorations of black lines have to be continuous across edges. And the second rule is that whenever you have two charges opposite each other on an edge, if they both have a clockwise orientation, then we require the charges to be opposite. Okay? So I'm going to put a bigger version of the tile here, and we're allowing reflection. So really we have these two tiles. So let's look at this second rule, because it is a bit funny. So what do I mean by this? Well, if you look at these two tiles, I've got these charges that I've highlighted in red, which only have an anti-clockwise orientation. So we consider those as being off and not playing a role. So a simpler picture is this one, where I've just got these two tiles, the black line decorations and these charges. And the rule now is simply that you're not allowed to put two pluses next to each other, and you're not allowed to put two negatives next to each other. Now, I think it's perhaps being a little cheeky to consider this as a single tile. When you flip it over, these charges are moving about. And I think it really is behaving much more like two tiles. On the other hand, I guess you could teach a child how to, these rules. So there's a sense in which it does feel like a valid rule, but for me, I think it's much more behaving like a pair of tiles. And this comes back to what Kyle was saying about how do we actually count the complexity, how do we count how many tiles we have. I think it's certainly two tiles though, and although it's not one, it would be great if it was one, there are still not that many aperiodic tile sets with only two tiles. So I think it's still quite cute with just these simple rules that this forces aperiodicity. And by the way, because I'm not using reflections anymore, where we just have these two tiles, you can actually replace the black line decorations with bumps and dents. So the question is how we put these together to form infinite tilings. So here's a picture. I've labelled the flipped tiles in grey, and if you squint, you can see various structures. This is always a good tip, by the way, for people getting into aperiodic order. Look at pictures and squint, and you can start seeing other features that you might not. You can see that the charge decorations, for example, they follow these lines. Right, so what I wanted to do, just checking the time, is to run through a proof of aperiodicity for you of this. Because for my money, it's a very simple proof and a bit different to other proofs of aperiodicity I've seen before. So the theorem is that valid tilings using translates or rotations of these two tiles are necessarily non-periodic. So here's the proof. So I'm going to orient these black line decorations so that we always travel anti-clockwise around our triangles. Okay, so if we're moving along one of these straight lines, the offset that we're towards is on our left when we're traveling around these. And I'm going to use that to assign charges to my tiles. So I'm going to think of these tiles here as positively charged. It's the charge at the exit of each tile as we're traveling along this line. Okay, so this is a line of positive charges. And then the following observation is completely trivial and obvious. If I've got a sequence of straight line decorations, well, they all have to have identical charges, because remember, I rule out that a plus meets a plus. So if that one's a plus and I meet another straight edge there, that also has to be a plus, that has to be a plus, that has to be a plus. So each edge of our triangles all have edges which can be consistently assigned charges. I would let CH of E denote the charge of each edge, which is either a plus or a minus. Okay, trivial observation. The next one is that edges, their charges enforce charges of other edges. So I have this notion of an edge leading to another one. So the idea is that we imagine we're on a train going along our edges, but we're going way too fast. When we hit the turn, we don't go around the turn, we crash off the tracks, and we bump into the other edge. That's what I mean by one edge leading to another. So this edge E1 here leads to this one, E2. Now, that offset can either be near or far. And it's very easy to prove that if the offset is near, like in this left-hand picture, then the charge of E1 must be the charge of E2. Right? So if that charge there is C, the right-hand one is C star, well, that enforces this one to be a C, and this is a C-charged edge. A C star-charged edge. I should have really swapped these. So both of these are C star. Whereas if I'm offset far, it's the same situation, but now, because I'm travelling anti-clockwise around triangles, this edge E2 is now the opposite charge of E1. And it's this second condition here, that if I lead one edge to another one with a far offset, then I have to flip charges. Okay, that's our second observation. Our third observation is that therefore we can't have a chain of three far offset edges. I can't have E1 far offset to E2, far offset to E3, far offset back to E1, because it's supposed to flip charges every time, and that doesn't mix with parity 2, having a cycle of period 3. Okay, very clear. Now, this is the main crux of the argument. I claim that edges must always lead to longer edges. If we don't have that, we create spirals of cycles of 3 edges, which we've just seen can't happen. So why is this the case? So suppose that I've got a red line here, which is leading to a blue line down here. Now, by the way, that blue line, so I'm assuming that it has the same number of tiles or fewer than the red one. That must be far offset from the red line, right? Because if it wasn't far offset, I'd have to be angling it in this way, and that turn would then bump into the red line. So because the blue one has fewer tiles, we better have that it's far offset, as in this picture. Okay, so the red line meets far with the blue one. Now, eventually that blue line turns. So where does it go? What edge is that leading to? This one. Now, what can happen with this line? I can add a few tiles, and if I keep going, then I'll eventually bump into the red line. And then I've got a cycle of 3 edges. We can't have that, so we better turn at some point. So maybe I get this far and I turn. Okay, that's not going to save you, because I then lead to another edge, say that one. And if I bump into the blue line, then I've got a cycle of 3 edges. Not allowed that, I better have another triangle. Well, this isn't going to last too long, right? Eventually I get trapped in this 3 cycle of far offset edges, and we've already seen that you can't have that. So therefore that blue line must be longer than the red line. Or the red line could be infinite and the blue line could be infinite. That can also happen. Okay, is everyone happy with that? If there's anything that's not making sense, please let me know. Right, so it then very quickly follows that there are arbitrarily large but finite triangles. Okay, so if you just follow some edges, the edges are getting longer and longer and longer, so there are arbitrarily large triangles. That's a little bit of an oversimplification, because I could end up bumping into an infinite line, and then I'm just on an infinite line. So you need a little bit more work just to show that the case where you have infinite lines doesn't save you. But from the fact that you have that one edge always leads to a longer one, it follows very, very easily that you have arbitrarily large triangles. And as I've already described, if you have arbitrarily large triangles, you can't be periodic, because suppose that my tiling T is preserved by translation by x, this non-zero translation vector. Well then, as long as I have a triangle with height bigger than the magnitude of this x, well then there's going to be the triangle overlapping with itself when I translate it. But when I translate my tiling, it's supposed to preserve all triangles. So by contradiction, we see that x can't be a translational symmetry of our tiling. So that's the proof. I think that's a pretty simple proof and quite different to others that I've seen before. And the crux of the argument is this one. I don't know if there are any other examples where this kind of argument could work. I mean, it seems pretty specialist to this example, but I don't know. Maybe there are some other cases where you've got some kind of quantity that has an incompatible kind of cyclic nature to constructing some kind of geometric spiral like this, and some quantity that's incompatible with that. Right, so that proves non-periodicity. I hope that was convincing. You should also show that there exist valid tilings with these rules, and that's actually pretty easy. So and that's usually the case, right? It's easier to show existence of these tilings than it is to show non-periodicity, usually. So to show that there exists such a tiling, we start with an arrowed half-hex decoration, by which I mean one of these decorations of Sierpinski triangles where you've got triangles of arbitrarily large size. What I'm going to do is I'm going to construct an edge graph. And again, it's the same idea. I imagine going on my train along these edges way too fast. Instead of turning, I always just fall off the edge and bump into the edge it leads to. And that gives you this graph here. I hope it's big enough for people to see. Can I? Oops, no. I was trying to zoom in, but I'll not tempt fate. So hopefully you can see that. I've decorated the parts where I fall off with either blue or red. So the red ones are far offset and the blue ones are near offset. Now there are no loops in this graph, right? Because edges always lead to longer edges. So I can't have a loop, because then I'll be leading to an edge of the same length at some point. So because edges always lead to longer edges, we have a tree, or at least a union of trees, and that means that I can assign charges so that the charges always flip sign at far offset or preserve sign at near offset. Right? I just put a charge anywhere on this graph, and then that determines where the charges are everywhere else. Okay, so I can make sure that the charges are consistent when I do these edge transfers, and there are only 3 other cases to think about. So the only other 3 cases are that 2 straight edges meet, but we've dealt with that because we know that the charges here are opposite by the way we've consistently assigned charges to edges. Another case is that I've got a straight edge and then I've got to turn into it, but there are no charges over that edge at that turn, so there's nothing to check for that case. And the other case is that I don't have an edge involved at all at 2 meeting tiles, and again, we only have 1 charge of that edge. There's nothing to check. Okay, so just making sure that I consistently assign charges to edges and that the transfers are correct. That means that it's a valid tiling. So that proves that these things exist. I feel like I'm overrunning time, so shall I just finish off with one last slide? Sorry. One thing I wanted to quickly mention here is that, again, there's a substitution rule which generates at least a minimal core of this tiling space. I feel like we really have a pair of tiles, although they're 2 tiles that look almost identical. It's just up to this charge swap. And flipping charges, if you flip charges of a valid tiling, you get another one. And you can consider the quotient space. That quotient space is actually a model set, just like the Penrose 1 plus epsilon squared and the Taylor Socolar tilings. So these are all model sets, and they factor, so this is more for the experts, they factor to the 2-dyadic solenoid. Whereas for the hat tiling, as I think Lorenzo will explain in his talk, this is also a model set, but it factors to the 4 torus. So it's more a quasi-periodic structure, whereas these are limit periodic. So although they look relatively similar, they're aperiodic tile sets of very few tiles, and there's some hexagons there, the foundations of them, that's about where the similarities end. They're completely distinct structures, and I think that makes the hat tiling all the more remarkable. We've had these other contributions, but this one is something completely new, which I think is amazing. I'll stop there. Thanks.
Are there any questions? Yes?
I have a remark and a question. The Taylor Socolar tiling and the Penrose 1 plus epsilon squared tiling, they are not directly related, but they have a common, more complicated ancestor from which they are both locally derived. So in the sense of dynamical systems, they are 2 different factors. Now the question, have you investigated what the relation of your tiling to Taylor Socolar and or Penrose is?
Not so much.
The hierarchy of triangles which they all have in common.
They factor in a very different way to the NEF. So the five, where it's not 1-to-1, there's a completely different structure. So I imagine there's almost no relation. But I know that so I think on the other side I mentioned that the Penrose 1 plus epsilon squared and the Taylor Socolar, if you look at how they factor to the NEF, they're almost identical, and the dynamical zeta function is identical for the 2. But they have different cohomology. So they look at first like they're very similar, but actually they're distinct. I think that this one here is completely different. It's also achiral, so there's a handedness to everything, whereas those 2 have this reflection symmetry. So I feel like there's very little in common with this embellishment of the half-hex to those 2.
Thank you. One more. We have time for one more question. Yes?
I think someone could ask the obvious question. Have you tried to realise these tiles physically using magnet?
I wanted to mention that. So, okay, the charges, they might seem like a bit of a bug. It's nice to have geometric rules. But on the other hand, you could think that it's a feature, something quite nice to play with. You know, get a box of these, throw them in, see what happens. We were working on trying to simulate, so randomly attaching tiles and see how well it builds things up. I mean, the hat tiling, as we've seen, it's very hard to build large patches of it. With this, you can really see the structure. It's actually pretty easy to build massive patches, knowing what you're doing, knowing how to do the charge loss. So my impression is that if you did this physically, it would self-assemble quite nicely. I don't have any physical tiles or magnets, but I think that would be lovely to do that. Yeah, thanks.
Thank you. Thank you very much, Jamie, for the very interesting and accessible talk. And let us thank the speaker once again.